Okay. So, um, yeah, really the last group of types of things that I might ask you is about Laplace transforms. Um, I may ask you to find the Laplace transform of a function. I may ask you to find the inverse Laplace transform of a function. I may also ask you to solve a differential equation using Laplace transforms, which would, I mean, if I do that, then that requires you to do both of the previous two. Um, but anyway, let me do one of each. So, first of all, there's finding a Laplace transform, which should be fairly straightforward um, because once again I'm making this test open book and you have this chart. So this should take care of what you need. So the first one is easy. I just sort of break this apart. The first thing I'm looking at is a t. So the Laplace transform of t is 1 over s squared. So 1 over s squared, good. And then I've got minus 2 times e to the 3t. So first of all, this minus 2 is just going to carry right over. So now I just have to write, like, whatever the Laplace transform of e to the 3t is, we'll just go here. But the 2 carries right over, and the minus sign carries over. Now, e to the 3t should be 1 over s minus 3. And that's it. That's all there is to that one. There's also finding an inverse Laplace transform, like this. Now, again, you are going to have this chart, but then what if we're looking at something that doesn't quite look like anything on the chart? Um, Roughly speaking, I see a quadratic in the denominator, so I'm kind of looking at these sines and cosines, but for these sines and cosines, it's like there's no s term in the bottom. There's an s squared term and there's a constant term, but there's no s term in the bottom. I have an s term in the bottom. Typically, what this means is that there's going to be some possibly partial fractions and or completing the square. So I don't know, let's think about it. Do we need to do partial fractions? I would try to factor the bottom, and I am not thinking of how. Let's see if the bottom factors at all. I mean, I can use the quadratic formula. But if I'm getting a complex number, then I'm going to give up because we don't really do complex numbers in partial fractions. If it only has complex roots, then I declare that it just doesn't factor for our purposes here. And it does look like it's complex, because this would be 16 minus 20. So let's give up on partial fractions. That means that we should be completing the square. So s squared plus 4s plus 5 is... Woo. Okay. I take half of this number, so 2, and that's why this is a 2. Of course, if I squared this would give me s squared plus 4s plus 4, and I actually had plus 5, so I need an extra 1. So now I've completed the square. So where are we now? This is s plus 2 squared plus 1. Now, what I'm thinking right now is along the lines of translation, which is like, yeah, this 10-3 stuff. Yeah, it's like this formula. If there's an inverse Laplace transform that I know, and I would like to plug something else inside, like s minus a instead of s, then I can do that. I just take the inverse Laplace transform little f and I multiply that by e to the at. And actually, in the book, there's even this table with specific examples of that, which is really helpful. So what I have looks a lot like, I'm not sure which one of these it is. It's either the line 2 or line 3, the cosine or the sine. Because if you look at the bottom, I have like a completed square. It's like my a is -2 and my k is 1. So I like that. So here's what I want to do. If I have s plus 2 in here, I would like all my s's to be appearing in s minus, or in s plus 2's. So what do I mean? I don't like this s all by itself. I would like this in parentheses as an s plus 2. Of course, I can't just do that. That changes things because this is 4, what I had was 5, so I make up the difference. And in fact, let me write this. There's not going to be a lot happening in this step, but all I'm doing is I'm breaking up the numerator of the fraction. So now I'm ready to go. This is like this one, where a is -2, and this 2 is just extra, so that 2 will just carry right down. So I am going to have a 2 from this 2, and then it's e to the at cosine kt. So a is -2, k is 1. So e to the -2t cosine 1t plus whatever the inverse Laplace transform of this is. And now I look here, and that looks like k is 1 and a is -2 once again. So I'm going to have e to the -2t sine kt. Yeah. Okay, good. So then, let's solve a differential equation. And it is likely that I will give you a hint. Because often solving these involves partial fractions. We almost had to do partial fractions last time, but we didn't really have to do it. But it often involves partial fractions, and I don't want the problem to just be a big partial fractions problem. I know that I've tested your partial fraction skills in multiple ways. So it's likely that I will give this one a hint if I feel that you need it, or if I feel the partial fractions would be too hard, I will just tell you the partial fraction decomposition of something. And this hint it's first of all, it's a hint to tell you how to do a particular step. Also, if you don't find the hint helpful, that probably means you did something wrong. So the hint gives you a way of telling that maybe you did something wrong if that's the case. Anyway, let's solve this. I'm going to do the Laplace transform of both sides. To do this, you have to remember, or once again, because this is open book, just look it up, this. So what's the Laplace transform of y double prime? It's going to be s squared times the Laplace transform of y, and I just use a capital Y for the Laplace transform of little y. And then I have to subtract, there's the next power of s down times f of 0, or y of 0. So the next power of s down would just be s times 1. And then minus, and now I do the next power of s down. Of course, the next power of s is this is going to be the last one because I'm down to s to the 0 times y prime of 0. Okay. Plus 2 times the Laplace transform of y prime. Okay, what's the Laplace transform of y prime? It's going to be s times the Laplace transform of y minus, and then I do the next power of s down, which is s to the 0, times y of 1. Or, sorry, y of 0. Plus 2 times, and this is just the Laplace transform of y, equals, okay, what's the Laplace transform of e to the t? Well, we have our table. Our Laplace transform of, e to the at is 1 over s minus a. So this is 1 over s minus 1. Okay, so we did the Laplace transform of both sides. I'm going to collect all of the parts with a y on it. So I've got s squared y, I've got a 2sy, and then a 2y. I'm going to move everything else to the right. So I have a plus s on the right. This would be a plus 2. This would also give me another plus 2, so plus 4, plus what was already there on the right. Okay, so y would be that over that. And this is where we would, first of all, I would simplify this. So I'd kill the fraction, I would multiply the top and the bottom by s minus 1, and then I would have to do partial fractions because my denominator would have not only this, but an s minus 1 on the bottom, and I would have to do the decomposition. Fortunately, and this is where the hint comes into focus here, I told you the partial fraction decomposition of this exact thing. And this is where, if I got something slightly different here, and it really wasn't the same as this, then you should know that you did something wrong. Either that or I made a mistake, but I'm going to be very careful about this part. So we got that. Now all that's left to do is to find the inverse Laplace transform of this. Oops, well, we're not ready. I should play with this a little bit. This one is no problem. The 1/5 I can carry right down. The inverse Laplace transform of 1 over s minus a is just e to the at. So I know what's going to happen with this part. This part's not so clear, but this part is similar to the last example that we did. It's going to be partial fractions. This is already the partial fraction decomposition. This denominator will not factor. If you try it, you'll only get complex roots. So what we should do is we should complete the square. And let me try to do this maybe a bit faster than I did last time. This will be s plus 1 squared, is 1 because it's half of this 2. If I squared this, this would give me s squared plus 2s plus 1, but I wanted a 2, so I put that there. Okay, now on the top, I'm not going to write 4s plus 17. Well, I am, but it's going to look different. Now I'm thinking along the lines of like the fact that if I have an s plus 1 here, then I want all my s's to appear as s plus 1s. So I would like, instead of this s, I would like an s plus 1. Of course, now I have to run around and think about what I have to do to fix the fact that I changed that. This 17 can become a 13, and then that way this, 4 times 1 plus 13 would be 17. So this is the same thing. Okay. Now I think I'm ready to go. I think I'm ready to find little y. So first of all, I have this part. Oops. This part looks like this. A is -1. So first of all, this 4/5 is just a constant, so I can ignore the 4 and the 5. Other than that, A is -1, K is 1, so it looks just like this. So, like I said, the 4 and the 5 can just carry right down. And other than that, I have e to the at cosine kt. Okay? Plus, now I would have this part. I don't want to really draw a circle around it because it's going to mess up the picture, but 13 over this. So when I'm doing 13 over this, first of all, 13/5 is just a constant. And other than that, I can act like this is a 1 over this, which looks like this. Because k is 1 and a is -1. So 13/5 e to the -t sine kt. And then we had this. 1/5 is just a constant. And the inverse Laplace transform of s minus a is e to the at. So this one would be e to the positive t. So that's it.